All right, welcome to Chapter 7, Section 4, Evaluating Logarithms and Graph Logarithmic Functions. First of all, logarithm of y with base b. This is denoted by the fact that you would take the log with a subscript of b to y. So this is log of y with base b, or log base b of y. Basically what you need to know here is that b and y are always going to be positive. A common logarithm you would write like this. It is assumed that base 10. So anytime a log is not written, a base is not written, you assume it's a base 10. A natural log is a log with a base e, and we got done talking about e as being the natural base. So for a natural base, it's e, and it can be written as ln of y. ln and log base e of y are equivalent. Definition of logarithm with base b. Basically what you've got here is that log base b of y is equal to x. If and only if b to the x power is equal to y. And the expression log base b is read log base b of y. Now there's, I think, an easier way of figuring this out. If you have a log base b of y, there are things that are called inverse operations. So, rewinding from a long time ago, plus is undo minuses, and vice versa. Multiplication undoes division. And x to the squared, you undo a square power with a square root. Right? Logarithms have a inverse operation. To undo a log base b, you undo that with an exponential with a base b. What that means is, from 7.1 and 7.2, we dealt with the fact that you could have 2 to the power of x. 2 to the power of x equals y. This is an exponential with a base 2. Now, according to what I wrote right here, a log with base b is undone by an exponential with base b, and vice versa. So to undo a 2x, to undo a 2x, 2 to the x power, you put it to the log base 2, 2 to the x power. This stuff right here then cancels. So this part here cancels, and x is equivalent to log base 2 of y. So you're going to be doing some examples that you have to convert from logarithmic form to exponential form. Well, look at this. If this is equal to x, well, this is a log base b. Log base b is undone by an exponential base b. So you make this an exponential, b to a power, b to a power. The exponential and the log cancels, and all you're left over with is y equals b to the x. And that is the definition right here. That is the definition. So take a look here. You can try to use the definition if you want, but remember, log base 2 is undone by an exponential base 2. So you're going to raise this to a base 2 power. Rewrite this, 32 is equal to 2 to the 5th. What undoes a log base 7? a base of 7. So 1 equals 7 to the power of 0. What undoes a log base 13? A 13 base. So 13 is equal to 13 to the first. What undoes a log base 1/2? Well, that would be a base of 1/2. So 2 is equivalent to 1/2 to the negative 1 power, which is correct. Please notice that this part here cancels, this part here cancels, this part here cancels, this part here cancels to give you your exponential form. So, rewriting an equation in exponential form. Pause this, try this on your own. So pause the video, see if you can do it. I'm going to move on though and say that log base 18. Do not forget to undo a log of a base b, you exponential base b. So log base 18 exponential base of 18. So 1 equals 18 to the power of 0. Here, log base 2. You make this into an exponential by doing base 2. So 64 is equal to 2 to the power of 6. You have converted it into exponential form. So take a look at guided practice number 1, 3, and 4. Number 1, log base 3 of 81 equals 4. Put it into exponential form. All right, well, if we convert it to exponential form, we raise it, we make it a base of 3. This cancels, which leaves us simply 81. 3 to the power of 4. Number 2, or I guess number 3, log base 4 of 1 equals 0. And I don't know how many times I can say it, but to undo a base, log base 4, you do an exponential base of 4. So log base 4, or 4 to the power of log base 4 cancels out, and 1 equals 4 to the power of 0. Oh, well, this is actually 14, but you get the idea. So number 4 tells us log 1/2 of 32 equals -5. So what base would undo a log base 1/2? Well, 1/2. A base of 1/2 undoes the log base 1/2. And 32 is equal to -5 to the 1/2 power. That's it. That's how this goes from logarithms to exponential form. Now, evaluating the logarithm. There are 2 ways you can do this. One would be to write this in exponential form. Like I said, you could write it in exponential form. So this first one, if we said let this equal x, you could say to yourself, how do you undo a log base 3? Power, a base of 3. So 81 is equal to 3 to some power. Now you can in your head decide what is x. Okay, 3 squared, 3 cubed, and so on. You know, that is the way you could set this up. So here, log base 4, put it to the 4th power, the 4th base. So 0.25 is equal to 4 to the power of x. And you'd have to figure out what exponent works for here. That is if you wanted to do it by hand. In the next couple sections, you can use the calculator, and you can use something called the change of base formula. Change of base formula is going to help you evaluate and graph logarithms. The change of base formula tells you to take log base b of y equals x and Base b could be anything. And you're going to change of base using, you use common logs or natural logs. So this right here, you would take the common log of y, divide by the common log of b, and that now is what x is going to equal. That's how this is set up. And you're going to want to, of course, put parentheses around the top things. So for letter C, you could do common log of 256, divide it by the common log of 1/4 to get your answer. And for part C, the answer is -4. For part D, you would do log base 7 over log 49, and you would end up with 1/2 as your solution. All right, evaluating using the calculator. So right now, use the change of base formula. So that you can know that you just evaluate log 9 over log 1/3 to get -2. Log 4 over log 16 evaluates to 1/2. This is how the change of base formula will help you. Guided practice 5 to 9. We probably actually won't do all of them because we're just evaluating using the change of base formula. So let's take a look at 5. 5 says log 2 of 32. So on your own, pause the video, and on your own, come up with the change of base formula. So you take log 32, you divide it by log 2, and you should get 5. Number 8, ln of 0.75. You don't even have to change this. You don't even have to use the change of base formula. Find in your calculator where it says ln, type it into your calculator, and you end up with -0.288. Change of base formula should be helpful for you. All right, using inverse properties. This is how I gave you the definition of logarithms. Inverse property. Look here. This is a base of 10 with a log base 10. So for part A, all you're looking at is the fact that a 10 to the power of log base 10 undoes each other. They cancel out. So A is just 6.7. This one here is going to be a little bit tricky because this is not the same base. This base here is 16, this base here is 2. They are not the same. But let's think about the number 16. 16 is 2 times 2 times 2 times 2. So you can rewrite 16 as log base 2 of 2 to the 4th x. And this right here makes you happy because log base 2 of 2 cancels out. 4x is your answer. That is the best way, not necessarily using the definition, but actually doing the inverse properties to help you solve those. All right, so finding the inverse now. Just like a section in chapter 6, the first step is to switch x and y. So step 1, switch x and y. Number 2 would be to solve for y then. So right here, first switch x and y. Now think to yourself, how do you undo a log base 7 or a base 30 halves? Well, you make it an exponential. Because now log 3 halves to the log 3 halves cancels out. And your new inverse equation is 3 halves to the power of x. We have not used natural logs yet, but we need to look back at our definitions and know that a natural log is a log with a base e. So, to undo a natural log, you raise it to a base of e. All right, so step 1, switch x and y. Now, raise it to the power of e. So now you have e to the x equals a natural base and a natural log cancel, y minus 4. And now it's inverse operation of minusing. So you add 4 to both sides, and you get y equals e to the x plus 4. Make sure it's obvious that it's not x plus 4. It's e to the x, then plus 4. All right. Number 5 and 6 should not take you very long at all, because log base 10 to the power of log base 10 cancels out. Your answer is 7x. You can't, number 6, you cannot automatically cancel out. You have to rewrite this as log base 3 of 3 to the 3x. 3 cubed is 27. 3 times 3 is 9, times 3 is 27. Now, log base 3 of 3 cancels out, and your answer is 3x. Find the inverse function. Step 1 was to switch x and y. Step 2 is solve for y. Well, there's only one way to get rid of a base of 7. I'll say it again. You log base 7. Log base 7. So log base 7 is 2y. And you now have log x of log base 7 of x. So we're not quite done yet. Because now we need to divide by 2. So y is log base 7 of x divided by 2. The last one here from the checkpoint. How do you switch variables, of course? So x equals ln y plus 6. To undo a natural log, you raise it to the natural base, or by the natural base. So e to the x is equal to y plus 6. Of course, you're going to subtract 6 now from both sides. And so your final answer is that y, the inverse is y equals e to the x minus 6. Let's take a look at guided practice number 10. Guided practice number 10 says just 8 log, 8 to the power of. So 8 is the base. And then up here you have log base 8 of x. So 8, base of 8 undoes a log base 8. simplify it to just x. Number 12, log base 2 of 64 to the x. To undo a log base 2, you put a power or an exponential of base 2. Oh, I'm sorry. I'm getting ahead of myself here. You can't just do something. You have to figure out how to make 64 into a base of 2. So 2 to what power gives you 64? Well, 2 to the 6th power gives you 64, and then to the x. So log base 2 of 2 gives you 6x. So please remember that logarithms undo exponentials. All right, graphing. There's a few pieces of information you need to remember for this. First of all, the graph of y equals log base b of x is shown below. B, of course, is greater than 1. And for b is between 0 and 1. So, because y equals log base b and y equals b to the x are inverse functions, the graph of y equals log base b is the reflection over the line y equals x. So, in this case, x is greater than or equal to 0, and the range is all real numbers. So, we just got done talking about exponentials. And in exponentials, the domain had been all reals. And the range was y greater than or equal to, I'm sorry, not or equal to, greater than the asymptote. So for this situation, it'd be 0. So when we're dealing with the inverse of that, you now have to switch them, just like you would switch x and y, you switch domain and range, and they change. That's why range is all real numbers, and domain is now changed. So the parent function looks like this. So the parent function is log base b of x. The child function is log base b of x minus h and plus k. All right, that should help you with this. So basically what you're looking at now is for a logarithm, if this is equal to y, the exponential for this logarithm would be to put it to a base, to switch the variables and so on. But the information you need to know here is still that your asymptote is at k, but instead of y equals k, your asymptote is x equals k. Asymptote is x equals k, and the domain, or the domain is x is greater than k. It could be less than k if there was negative, but we'll see how that works out in a second. And you're still just going to graph it in your calculator. You may need to remember that you have to use the change of base formula in order to graph using your calculator. So let's look at some examples. So a bunch of this, the whole translation stuff, I wouldn't even worry about it. In your calculator, type in log y equals, all right, log 2 to the x. That change of base formula would be log x divided by log 2. So you can graph this in your calculator. You can come up with some nice points in your calculator. First thing I want to point out is there is no k value. So the asymptote goes through 0. X equals 0. You have some nice points like 1, 0, and 2, 1, and 4, 2. So 1, 0, 2, 1, 4, 2. The asymptote is x equals 0 right through here. So when I graph this line, it's barely gonna touch the asymptote. It's gonna look like that. So you don't have to do very much of this stuff at all. Plot several convenient points. So this is for part B. You're going to once again use the change of base formula. So you're going to graph log of x divided by log of 1/3. You're going to get some nice points like 1, 0, and 3, -1, and 9, -2. You're going to go ahead and plot those points. This is 1, 0, 3, -1, 9, -2. And you're going to end up with a graph that has an asymptote of 0 still, and takes a look like that. All right. Here's a translation. Listen, you again, do not worry about this part right here. Do not translate the graph. Just come up with the points. Type it into the y equals on the calculator. So you're going to type in now log of x minus 1 divided by log of 3. And then you can just add 2 at the very end. So again, log x minus 1 divided by log of 3, and then plus 2 at the end. And you should be able to come up with some decent points, like 2, 2, and 4, 3, and 10, 4, and plot those points. So 2, 2, 4, 3, 10, 4. And now you have, again, a graph that goes through like that. All right, I actually need to go back quickly and talk about the asymptote here. Okay. The asymptote for this. Since, remember we talked about that they're inverses, so exponentials, logarithms are inverses of each other, therefore the domain and range changes. But that also means then that the asymptote's not at k anymore, it's at h. Okay, so for this situation, it doesn't really change it all that much, but it's what makes this equal to 0. So go back in your notes, make sure you change this right here when we talk about asymptotes. I might actually add a new slide here. All right, so this is the parent function, and this is the child function. Log base b of x minus h plus k. All right, so for logarithms, now the range is all real numbers. the asymptote, instead of being y equals, the asymptote is x equals, and it's what makes this right here equal to 0. Well, that would be h. So x equals h is the asymptote, and then that means the domain is, for this, is greater than h. So, looking back at our problem here, we type into the calculator, example 6, log x minus 1 divided by log of 3 plus 2. That's how we graph the calculator. The graph's asymptote, remember, is no longer y equals. The asymptote is x equals a certain number. And its certain number is what makes this equal to 0. So all of you should hopefully know x minus 1 equals 0 means that the asymptote is at 1. And when you look at the graph, you would say that the domain is x is greater than 1. The range, of course, being all reals. So let's take a look at this. This is checkpoint number 9, or yeah, checkpoint number 9. This has to be viewed in your calculator. Since there are not parentheses around the x minus 3, it's log 1/2 of x. So, first off, let's do the stuff we know. The range is all real numbers for this. The domain is what makes the x term equal to 0. So, what makes x equal to 0? I'm sorry, not equal to, but greater than 0. So x is greater than 0. And as far as graphing is concerned, we just need to have a couple points. If you want to use a couple points, find them in your calculator. So some of the points here are 1, -3, and we'll say 4, -5. So 1, -3, 4, -5. And you end up with a graph that goes like this. So there's your graph. Here's the domain. Here's the range. The asymptote was at x equals 0, because it's what makes the thing with a log equal to it. All right, let's look at 16. Let's graph and state the domain and range of y equals log base 5 of x. So, in your calculator, put it in there as log base x divided by log base 5. This is the change of base formula. What is the asymptote? So for exponentials, it was y equals. For logarithms, it's x equals whatever makes that 0. So x equals 0 is the asymptote. Therefore, the domain is x is greater than 0. The range is equal to all reals. And now we have all the information we need. Just find a couple points to help yourselves out. And now you can graph. So find those 2 points. The 2 points that I found were 1, 0 and 5, 1. Those are some points that I would want to use. So you type that into your calculator. You put in there 1, 0, and then 5, 1. And your graph then looks like something like that. That's a good sketch. Let's take a look at number 18. 18 says that you've got log base 4 of x plus 1 minus 2. So, let's do the stuff we know. The range, all reals. The asymptote is x equals. What makes this equal to 0? The asymptote's -1. That means x is greater than -1. So, find 2 points. Those 2 points that you're looking at, you could use 0, -2. You could use 3, -1. And now plot those points. So 0, -2, 3, -1, an asymptote going through -1, so your graph would peak like that. All right, that should give you all the information you need to know for section 4. When you come into class, we'll go ahead and work through some more problems before you show mastery of it. Thank you.